In this video, I'm going to discuss the Kochen-Specker theorem. And so this is a theorem that puts constraints on what a hidden variables theory of quantum mechanics has to be. And so we'll see in the end that what it tells us is that a hidden variables theory must take what's called contextuality into consideration. And we'll see in the videos coming after this one when I discuss the pilot wave theory of quantum mechanics that the pilot wave theory uh, contends that they do take contextuality into account, and so therefore it is a valid hidden variables theory. But let's get into what the Kochen-Specker theorem says. So the Kochen-Specker theorem, which is sometimes called the Bell-Kochen-Specker theorem, so Wikipedia says of it here. So the theorem is a complement to Bell's theorem, to be distinguished from the Bell-Kochen-Specker theorem of this article. While Bell's theorem established non-locality to be a feature of any hidden variable theory that recovers the predictions of quantum mechanics, the Kochen-Specker theorem established contextuality to be the inevitable feature of such theories. And we'll see also when I talk about the pilot wave theory that they also contend that it is non-local. So it's non-local and contextual, and so it satisfies these constraints put on by the Kochen-Specker theorem and the Bell inequality. Right, so the theorem proves that there is a contradiction between two basic assumptions of hidden variable theories intended to reproduce the results of quantum mechanics, that all hidden variables corresponding to quantum mechanical observables have definite values at any given time, and that the values of those variables are intrinsic and independent of the device used to measure them. So this clause right here is talking about contextuality. So contextual being sort of the context of the measurement that you are performing. And so it's saying that there's a contradiction between sort of this quantum realism that says that these observables are telling us things about actual states of the quantum system, and not just actual states, but actual states that sort of exist independent of the measurement actually being performed. So the contradiction is caused by the fact that quantum mechanical observables need not be commutative. All right, so then the Kochen-Specker theorem excludes hidden variable theories that assume that elements of physical reality can all be consistently represented simultaneously by the quantum mechanical Hilbert space formalism, disregarding the context of a particular framework. So related to the experiment or analytical viewpoint under consideration. As succinctly worded by Isham and Butterfield, the Kochen-Specker theorem asserts the impossibility of assigning values to all physical quantities whilst at the same time preserving the functional relations between them. And so in this video, like I said, I'm going to be talking about what this actually means and sort of go through sort of a simplified version of the proof of this theorem. And so a lot of this can be somewhat daunting and complicated. So I came up here so this is kind of summarizing it, and then I'm going to go through a loose analogy that I came up with for this. So if you don't understand anything sort of that comes after this, just keep this in mind. So hidden variables theories, often abbreviated as HVT of quantum mechanics, says that prior to a measurement, however we want to define a measurement of an observable, there is some fact of the matter that is definitely true about the quantum system. So, like we've talked about before with the Copenhagen interpretation, it says that when you're not measuring the quantum system, there's nothing really true about that quantum system. But hidden variable theory says that there is something true about them, and those things that are true about them are, the hidden variables themselves. So the hidden variables had definite values, even if we could not directly measure those values. That's why we call them hidden. So contextuality says that it matters how we perform a measurement when measuring incompatible or non-commuting observables. So we think of the Stern-Gerlach experiment measuring the spin in the z direction and the spin in the x direction. So measuring in the z direction is one context, and measuring in the x direction is another context. So if it matters how we perform the measurement, then there was no fact of the matter prior to the measurement. or at least not one that we can simply be revealed by our measurement. Therefore, hidden variables theories of quantum mechanics that do not take contextuality into account cannot be true. All right, and so let's get to my loose analogy here. So say that you are driving in a northeast direction on what we can call like a quantum road here. So we're in the northeast direction, so with some angle to, I guess, the east direction theta here. So on our quantum road, and in this theta direction, the speed limit is 85 kilometers per hour. Uh, or you're driving on a road at 85 kilometer with a speed limit of 85 kilometers per hour, but the speed limit is being increased to 100 kilometers per hour above some, I guess, line of latitude here that we can define as y equals 0, which is sort of a step function speed limit increase. So south of this line, it's 85 kilometers per hour. North of it, it is 100 kilometers per hour. And so I actually have a little figure here that I made. So we're so if we're south of this line right here, then the speed limit is 85 kilometers per hour. When we're north of it, it is 100 kilometers per hour in this direction along this purple vector right here. And so let's say a quantum police officer right at the marker where the speed limit changes measures, and we'll say that they're measuring at time t equals 0, your northward component of your instantaneous velocity is being 100 kilometers per hour. So this is our police car right here. They measure your northward component as being 100 kilometers per hour. So remember, we're in kind of a weird quantum world here with quantum police officers. So they're not measuring your velocity in this sort of northeast direction, only measuring the northward component of your velocity at this time t equals 0. Could the officer pull you over for speeding in the 85 kilometer per hour zone, given that right at the speed limit change mark at y equals 0 right here, you were measured as 100 kilometers per hour in the northward component. So we're saying that in this direction right here, south of this line, the speed limit in the direction of this purple line here, of this purple vector, was 85 kilometers per hour. Then north of that, it's 100 kilometers per hour. And right at the line, the police car measures your velocity as being 100 kilometers per hour in this, in the northward component here. So could the officer pull you over for speeding in this southern area here where the speed limit was 85 kilometers per hour, given that right at the speed limit change mark, you were measured at 100 kilometers per hour in the northward direction? Similarly, could the police officer, the, I guess, quantum officer, pull you over for going over 100 kilometers per hour after the speed limit change, so in the north part? So, because we are moving in the northeast direction and your northern component was 100 kilometers per hour, we would assume there's some non-zero eastward component. And so even in the northern part here, if we're thinking classically, we could think of you going over 100 kilometers per hour. And so you're still breaking the speed limit here in the north part. So like I said, in classical physics, we would say yes, that this quantum officer could pull you over because, for one, the velocity, when we go from y equals south, so south of this line, to y equals north, so north of this speed limit change line, it has to be continuous. So the limit of our velocity as y goes to 0 from the negative direction and y goes to 0 from the positive direction have to be equal. And so that means that at the limit of your velocity as y goes to 0 from above has to be 100 kilometers per hour, then the limit as it goes to it from below at 0 has to be 100 kilometers per hour. And so you must have been going over 85 kilometers per hour prior to the speed limit increase. And so, just thinking about that intuitively, if you're moving in, say, if you were just moving in perfectly north and right at this line you were going 100 kilometers per hour, then you would know that, some tiny amount just before that line, it could not have been 85 kilometers per hour, because then there would be sort of a discontinuity here in your velocity, that you would be going 85 kilometers per hour and then instantaneously jump to 100 kilometers per hour. And so that's what I'm saying right here. And so two, the officer could get you for going over 100 kilometers per hour even after the speed limit changes, because if you were moving northeast at some velocity, which I'm calling this v sub ne here for northeast, then by the Pythagorean theorem, we have that the square of well, I guess the magnitude of that, which is why it's in these vertical bars here. So the square of the magnitude is equal to the square of the magnitude of your northward velocity plus the square of the magnitude of your eastward velocity. And so we're saying that you're traveling northeast, and so we have to have that this eastern velocity, this eastward component of your velocity, is greater than 0. And so we have to have that our northeast velocity is greater than, or the magnitude of the northeast velocity is greater than 100 kilometers per hour. And that's, like I said, if we're thinking about this in classical terms. But on the quantum road, all we know are the measurements, and that the two bases do not commute. And so the component of your velocity in the north direction and the component of your velocity in the east direction do not commute with each other. And so just given that your northward velocity, we know nothing about your velocity in the northeast direction prior to the measurement. And knowing that your northward velocity was 100 kilometers per hour does not tell you anything about your velocity in the east or the northeast direction. And so the quantum police officer could not say for sure that your northeast velocity was greater than 100 kilometers per hour. So say we have a second quantum police officer that measured at some time t greater than 0, so sometime, say, a second after the first quantum police officer measured your north component of your velocity. So we have the second quantum police officer at some time, say a second later, they measure the eastward component of your instantaneous velocity and found that it was 60 kilometers per hour. Then the two officers could still not pull you over because they are measuring your velocity in different non-commuting bases. So the officers could not just simply combine the incompatible velocities that they obtain. So the north one being 100 kilometers per hour, the east one being 60 kilometers per hour, and get that you were going 117 kilometers per hour, and therefore, going over the speed limit of 100 kilometers per hour. So now let us say that the two quantum police officers are proponents of hidden variables. The officers pull you over and contend that with the measured velocities of the northward component being 100 kilometers per hour and the eastward component being 60 kilometers per hour, it can be determined that your northern velocity and eastern velocity components give information about your northeast velocity. Namely, that since you were traveling northeast and that your northeast velocity was greater than 100 kilometers per hour, you must have been breaking the law when you were north of that line. And two, you definitely had a northward velocity v sub n that was 85, that was between 85 kilometers per hour and 100 kilometers per hour just prior to the speed limit change. And so even if we were just taking your northern velocity component into account, you were breaking the law when you were south of that line. But you are in court and you want to contest this ticket, and you know the Kochen-Specker theorem, and so you could use it to contest this ticket in quantum court with the following argument. So one, if the officers say you definitely had a northward velocity of 100 kilometers per hour when y was equal to 0, so right when you were on that line, then the context of how the measurement was taken matters, since given any of the northeast and northeast velocities do not commute with each other. So only obtaining your northward velocity component, and even if they added the eastern component at some time t greater than 0, the officers cannot possibly know your northeast velocity was, since the officers only have your velocity in the north and or in the east context, and so not the northeast context, which is the velocity that matters. So your velocity in the northeast direction is the only context the speed limit applies to. Since the speed limit, since these are since these are contextual, the speed limit up here, so looking back at this, only applies to this purple direction. So the context of, just the northward component or just the eastward component, the speed limit isn't applying to those. It only applies to this northeast direction here. And so having the speed limit in the north or the east components, the speed limit does not apply to the north, to the pure north or pure east components. And you could also argue, too, if the officer's going to argue that context does not matter, so they're saying that, that your northward component of your velocity is that the speed limit also applies to that or to your eastward component, then you had no definite northeast velocity prior to this y equals 0, so in the southern part of it. And so the officers do not know what your velocity was when the speed limit was 85 kilometers per hour south of that line, nor do they know what your velocity in the northeast direction was after the speed limit changed to 100 kilometers per hour, so when you are north of that line. So your northeast velocity during the measurement does not matter because that does not tell anyone what your northeast velocity is outside of being measured. So the speed limit is not the speed limit while being measured, but just the speed limit. And so your northeast velocity obtained by the measurement is inadmissible because measurements do not read off some pre-existing state, since no such state existed, but tells you that the state during the act of measurement. And so we'd see that this second one here is essentially saying that there are no hidden variables. And so if we want to say that there are hidden variables, then we have to take this contextuality into account here. And so that's what the Kochen-Specker theorem is saying, that that with this contradiction here, we either, if we want to keep our hidden variables, then we have to take this contextuality into account. Otherwise, we will have to abandon our hidden variables here. And so that's kind of the, I guess, take-home message for the Kochen-Specker theorem here. And so now on to the more complicated stuff. And so we can think of it this way. So hidden variable theories of quantum mechanics make the following claims according to the Stanford Encyclopedia of Philosophy entry on the Kochen-Specker theorem. So they're essentially claiming these three things for hidden variables theories: that there is value definiteness, so all observables defined for a quantum mechanical system have definite values at all times; non-contextuality, so if a quantum mechanical system possesses a property, so a value of an observable, then it does so independently of any measurement context. So in other words, independently of how that value is eventually measured. And then the observables here. So there is a one-to-one correspondence between properties of a quantum system and projection operators on the system's Hilbert space. So in other words, each observable has an associated Hermitian operator and vice versa. So the Kochen-Specker theorem says that there is a contradiction in these three postulates here. So this paper here by Barbar in 2017 put it this way, and it's essentially saying the same thing. So 1 here corresponds to the value definiteness, 2 to the observables, and 3 to the non-contextuality. So value realism, each observable corresponds to an element of physical reality, and the values assigned correspond to the set of possible outcomes, which is the set of eigenvalues for the corresponding operator. In other words, for any observable Q represented by the self-adjoint operator Q hat, we have that. So this V here is a function that sort of takes the operator to its eigenvalues. And so we have that this V function here on our operator takes it to some element of this set here, where this set is the set of all the eigenvalues for that operator. Yeah, so where this, like I said, are the eigenvalues of the operator Q hat. In particular, in order to reproduce quantum mechanical average, this is the expectation value of Q hat here. So we're finding the average value of our eigenvalue here. So value assignment on eigenstates, or more precisely on their dispersion-free versions, renders the corresponding eigenvalue. So we have that the eigenvalue for this operator here is equal to the eigenvalues for all lambda. So lambda here being our hidden variables. So linearity over commuting operators. So remember in the previous video, I talked about the von Neumann impossibility theorem, where he assumed that this could be true for non-commuting operators, but that was an assumption that he really wasn't allowed to make. So this is sort of saying, okay, now we're going to talk about only commuting operators. So the linearity over commuting operators, which they call quasi linearity, since it only works for commuting operators, is this. So this is just kind of the same thing we talked about in the previous video, where we get the eigenvalue for these two operators added together is just equal to the addition of the two eigenvalues here. So when these are commuting for all A and B that are members of the real numbers. Then non-contextuality. So value assignment to observables is non-contextual, being that all observables are assigned values simultaneously, regardless of what else is being measured with a given observable. And so Barbar here goes on to elaborate, saying that condition 1 up here assumes two things. First, it assumes that every observable is what they call a beable. I believe that was a neologism of John Stuart Bell, which is essentially just, so we talk about observables in quantum mechanics, which are values that you observe, and a beable is supposed to just be a value that sort of a non-observed system actually has. So it first assumes that every observable is a beable, so essentially saying that when you observe something, you're observing what its value actually is. You know, we're not just getting some observable that's sort of independent of what it actually is. And so it assumes that every observable is a beable, in other words, an element of reality that exists with a definite value at all times. So for example, the electric and magnetic fields E and B are beables of Maxwell's theory. That is the realism part. Second, it assumes that these values are revealed faithfully in a measurement. This gives the value part. Since the set of outcomes of a measurement of a certain observable is the set of eigenvalues of the corresponding operator, it immediately follows that the values assigned to observables in the hidden variable theory must belong to their respective sets of eigenvalues. And so that's kind of a long-winded way of saying that when you measure something, you're measuring some value that actually existed independent of your measurement, that it was a real value that your measurement just sort of read off from the system. So condition 2 up here, this linearity over commuting operators, so this quasi-linearity, is a weaker and more physically plausible version of von Neumann's linearity condition that applied to all operators, not just commuting ones. So Bell refuted von Neumann's condition by arguing reasonably that a linear combination of incompatible observables cannot be measured by a linear combination of their corresponding measurement devices, since the two devices are incompatible as well. And so, if you have like two Stern-Gerlach devices sort of put in a row, and one is measuring in the z direction, the other in the x direction, we can't put those as like a linear combination of observable because they are measuring things that are not commutative, so they're not compatible with each other, is what they mean by saying sort of a linear combination of their measurement devices. So while condition 2 is physically plausible to assume, it is interesting to note that it can be deduced from condition 1, but we need to assume it explicitly because it can hold independently of condition 1. There is an important rule that can be deduced from condition 2. It is called what they call the functional composition rule, or FUNC for short, which states that if we have some operator here that we can get from this operator. So this f of this operator here is just a function that maps the operator b to the operator a. And again, remember this v here is mapping our operator to its eigenvalue. So if we have that a is the mapping of some operator here, B, so we have this mapping of B that takes us to this operator A, then the eigenvalue of that operator A is the function of the eigenvalue on B here. And so we can get this composition here of essentially this V here. And so we just apply V to A, then it applies V to B inside of this mapping to our operator A here. Funk tells us that the value map has to preserve the algebraic structure of the operators. In other words, the algebraic relations between values of observables mirror the algebraic relations between respective operators. You can check out this here if you want to see sort of a proof of this. And as usual, the lecture notes will be linked to in the description down below. So if you want to look over this yourself and click on these links to see my sources, you can do that if you want to. Because like I said, I'm trying to sort of simply describe this here. And so there is more nuance to a lot of this than what you'll get just from this video. All right, so condition 3, the non-contextuality, can be seen to naturally follow from condition 1, since value realism implies that all observables possess sharp values prior to measurement. In other words, elements of reality exist with sharp values regardless of being observed or not. But here we state it explicitly to emphasize the word observable used in the definition. And so, given these three postulates, the Kochen-Specker theorem can then simply be stated as there are no non-contextual, quasi-linear, dispersion-free states. This means that we must reject one of the above postulates of hidden variables theories of quantum mechanics. Then Wikipedia sums it up this way. So the theorem proved that there is a contradiction between two basic assumptions of the hidden variable theories intended to reproduce the results of quantum mechanics, that all hidden variables corresponding to quantum mechanical observables have definite values at any given time, and that the values of those variables are intrinsic and independent of the device used to measure them. Or to make it even more concise, a hidden variable theory of quantum mechanics forces someone to take contextuality as an assumption. And so this paper, Rajan and Visser say of the Kochen-Specker theorem, that the Kochen-Specker theorem, so as originally proved by Kochen and Specker, was originally proved some 50 years ago, I guess from 2019, by explicitly finding a set of 117 distinct projection operators on three-dimensional Hilbert space, then showing that there was no way to consistently assign values of 0 or 1 to these projection operators. Then this one that I've been following here, this bar 2017, says it this way: so it is impossible to note that the contradiction between the three postulates arises only for what is called non-maximal observables or non-maximal operators. So a non-maximal operator is an operator that is degenerate, so it has repeated eigenvalues, while a maximal operator is an operator that has non-degenerate eigenvalues. So we can show that this A hat is non-maximal. Then we can write this as a mapping from this maximal operator B hat here to A, and a different mapping from this C hat here to A, where B and C are non-commuting. So yeah, B hat and C hat are maximal operators, while F and G are Borel functions that take B or C to our operator A. By applying func and equating both sides, we get this. So the eigenvalue of our A is equal to the eigenvalue of B mapped to the eigenvalue of A using F, which is equal to the eigenvalue of C hat here mapped to the eigenvalue of A with this G function right here, which is the core of the contradiction. To see that, recall that the value assignment problem was concerned with one-dimensional projectors, which are highly non-maximal. The problem was that we demanded that the projectors get assigned the same value no matter which set of orthogonal operators it was considered to be a part of. This is equivalent to considering a projector as a function of different non-commuting maximal operators. And so this is because it's simply assumed that the observable to operator mapping is injective, so 1-to-1. So if we have this function here that maps our observables to our operators, sigma here. So from the observables to the Hermitian operators, 1-to-1. So each observable has just one operator. But if we have this here, then it's not injective, since we have this function here and this function here, both taking B and C to our A operator here. So as Barbar 2017 puts it, to illustrate this, let O be the set of all observables and let sigma be the set of all self-adjoint operators. Our hidden assumption was that this was injective. Now let us consider if that was not the case. So let us return to equation 51.15 from above. So that was this one right here, which I've just copied down right here. So we have that this A operator here is the mapping of our B to A with this F mapping. And then it's the mapping of C to A with this G mapping, where B and C are non-commutative. And we say that X and Y are elements of these observables, so they are two somehow distinct observables, such that the mapping here of X is equal to this F of B here. So it's equal to A, which is kind of what we're showing down here. And it's also equal to this mapping of C, which is also what we're showing down here. So in other words, the two distinct observables are mapped to the same self-adjoint operator A, but they are distinctly defined by their functional relation to operators B hat and C hat respectively. But what is the nature of this distinction other than being algebraic, since if we consider them as related to A hat, we can just assume that phi is injective, as we usually do, and say that they are observationally the same? The answer is that if they are really two different observables, then the difference must be ontological. Therefore, the value assigned to each one need not be the same. And so we're saying that with these two non-commuting observables here, their eigenvalues are not equal to each other. So if they are not equal to each other, then the eigenvalue of these mappings here are not equal to each other. And if that's true, then the mapping of the eigenvalues are not equal to each other. And this rescues us from the contradiction. So this above result is what this author here in 1987, Michael Redhead, called ontological contextuality. But how does the measurement context come into play here? To answer this question, let us elaborate more on what the ontological difference between observables really means. So far, we have been using the notions of observables and beables interchangeably, but now we need to note the distinction between the two. Observables are things that, well, could be observed using the physical process that we call measurement, while beables are the elements of physical reality attaining definite values at all times. The usual assumption is that a certain observable tells us direct information about a unique beable. This is one-to-one observable realism, so that injective sort of assumption above. So in other words, each observable corresponds to a unique element of physical reality, which we drop here to escape the Kochen-Specker contradiction. The ontological difference of our A as being a mapping from B and A as being a mapping from C then means that the observable A actually corresponds to two different and also here observationally incompatible beables, behaving observationally similar in different measurement contexts. So in other words, on an observational level, it seems we are getting information about the same element of reality that can be measured in two different ways, but in essence, each way reveals information about different elements of reality. To illustrate, recall that we can simultaneously measure A with B or A with C, but not B with C. The two measurement schemes are incompatible and hence need different incompatible measurement instruments. Let's call them, I think that's a tau, so tau AB and tau AC respectively. We could think about the measurement using tau AB, for example, as an instrument that measures B and displays this outcome, then applies the function f through a physical process. The two measurements need not yield the same outcome. They are physically distinct processes using different and incompatible instruments, each of which is designed to reveal a certain aspect of physical reality, and this leads to the contextual dependence in this case. And so that was a lot of words, and I think it be complicated. And so to kind of break down what this is saying, so let's think about it in the way that this paper does. How do we measure the spin of a particle? So one answer is that we measure the spin by the spatial separation in a Stern-Gerlach experiment. So if we think of our A hat here in this above description up here as, say, the up or down position of the particle in the Stern-Gerlach experiment, so whether it actually shows up in this upper position or in this lower position here, then B could be the SZ, so spin in the Z direction, and C could be the spin in the X direction. Thus, although the particle is moved either up or down in the experiment, we are measuring two different things, namely the spin in the Z direction and the spin in the X direction. So if we look at this image right here, we can think of this as spin in the Z direction, but if we sort of turn this 90 degrees sort of, into and out of the page, then this would be in the X direction. But we are still measuring sort of the position moving this way or this way in the X direction, but we are measuring two different things using this same A, which is the sort of position operator here, where B is the sort of Z spin operator and C is the X spin operator. So we are actually looking at this state. So we have the Z position here in the up and Z in the down. And in fact, I should call this up and call this down right here. So this is actually the state of our particle. So it's in this sort of superposition here of being in the up position up here because it's spin up, or the lower position down here because it is spin down. So our measurement gives, so if we go from this where it's sort of in the center right here, and then we go to these upward position up here, that tells us it's spin up, or we can then go from this to the down position here, and so that is spin down. So what this means is that we are measuring the spin in the position context. So Barrett here notes in a footnote, actually, that the contextual properties are not robust intrinsic properties. Part of what this means is that the value of the contextual property one gets on a measurement depends on precisely how one performs the measurement. So we can think about this in kind of another way here, using what's called the Peres-Mermin square, and I'll be sort of following all three of these papers here to demonstrate this proof, or more accurately show why the contradiction arises using the spin of two entangled particles. We have the following set of operators. So this right here is just the identity operator of Pauli matrices. So the sigma x, sigma y, and sigma z. So the Pauli matrices for the x, y, and z directions of spin, where the eigenvalue of each is given by this. So this is just the eigenvalue v. So it's just a mapping to the eigenvalue here for each operator, thus giving us for two spin half particles. So they're two spin half, each one can be up or down, so that gives us a four-dimensional Hilbert space. We have the following 6 contexts. And so we have, so we're multiplying all of these eigenvalues here for each thing. So these are for each of the rows. So we have this row up here, then this row down into this middle row, and this bottom row here represented like this. Then if we do it for the columns, so this one right here is this first column on the left. This one right here is for this column in the middle. Then this one here is for this column on the right. And if you took these, if you took the commutators of these, what you would find is that we have to have -1 for this rightmost column right here. So the product of all of these would have to be -1. So where each column and row, so each of the 6 products above, forms a context of observables that can be jointly measured. So we're essentially saying that everything in this top row can be jointly measured, everything in this middle row can be jointly measured, everything in this bottom row can be jointly measured, and similarly everything in this leftmost column can be jointly measured, everything in this middle column can be jointly measured, and everything in this rightmost column can be jointly measured. And so these right here are all kind of saying the same thing, but I think that, in this video is already getting a little long, and these can be a little bit confusing. So I'm actually going to skip to my sort of simplification of this. if you want to read all three of these things, so from this Mermin 1990 paper, this Bedroni et al. 2023 paper, and from the Mermin 1993 paper, you can read that in the lecture notes, but I'll give my sort of simplified version of this. So let's think of it this way. If we assign definite values of +1 to each eigenstate, so these are eigenstates for each of these observables, since we need that the product of any two within a row be equal to 1, since each of these are 1, then the product of any two in each of these rows must also be equal to 1. So the product of the eigenvalue of A and B has to be equal to 1, of A and C has to be equal to 1, and B and C has to be equal to 1, and that's what this is showing. And then likewise for each of the other rows. And that has to be the case because we want any of these rows to be commutative, because we want those to be compatible. You can get simultaneous measurements for each of them. And so we then get, for the sum of the expectation values of these eigenstates, that it has to be equal to 6, right? Because we have to have each of these be equal to 6 if all of these are equal to 1. But we know from the commutation relation that the third column is going to be equal to -1 here, which means that we need the following inequality for the operators, that if we add all of these up, that it's going to be less than or equal to 4. So say all of these besides the last one are equal to 1, so we have 1, 2, 3, 4, 5, then this one is negative, so we have to subtract it, so that gets us down to 4 here. And thus we get the contradiction that these have to be equal to 6, but they also have to be less than or equal to 4, and so it's saying that 6 is less than or equal to 4, and so that is a contradiction. All right, and like I said, that's essentially what all of these up here are saying, but they all kind of say it, I think, in a little bit more of a complicated way. And so I'm not just going to read through all of those. So the theorem of Kochen and Specker states that given a premise of non-contextuality, certain sets of quantum mechanical observables cannot consistently be assigned values at all, even before the question of their statistical distributions arise. So if a hidden variable theory satisfying these three postulates that we were talking about earlier were feasible, we would have a natural explanation for the statistical character of quantum mechanics, an elegant way of resolving the infamous measurement problem haunting all interpreters of quantum mechanics. What the Kochen-Specker theorem shows is that a hidden variables theory of the most straightforward sort, satisfying the three postulates, is not an option. The hidden variables program is left with only options that violate one or more of the three postulates. And so the main takeaway from all this is what I have here in red. Hidden variable theories of quantum mechanics must accept contextuality. The value of some properties, such as spin, that will be obtained in an experiment is dependent upon the context of the experiment. So it's dependent upon how the value is being measured. So Wikipedia sums it up this way. So quantum contextuality is a feature of the phenomenology of quantum mechanics whereby measurements of quantum observables cannot simply be thought of as revealing pre-existing values. Any attempt to do so in a realistic hidden variable theory leads to values that are dependent on the choice of the other compatible observables which are simultaneously measured. So the measurement context. More formally, the measurement result assumed pre-existing of a quantum observable is dependent upon which other commuting observables are within the same measurement set. So kind of that thing I was talking about earlier, where we measure the spin of a particle using its position in a Stern-Gerlach experiment. And so it has to be commuting with that position operator for it. So there are two ways we can think about contextuality. So there is what's called causal contextuality and ontological contextuality. Causal contextuality says that the act of measurement brings the state of the system into existence. And so the way in which the measurement occurs will cause a different kind of state to come into existence. And we'll see in the videos coming after this one that this is kind of the position that Bohmian mechanics, that the pilot wave theory actually takes here. Then there's also ontological contextuality, which says that the state measured must be understood as being part of a holistic system measuring device whole. And so its value depends on the kind of measurement being performed. And so this is kind of a loose analogy that I came up with for it. So think of the statement, a run on the bank. So what could this mean? So it depends on the context. So a run on the bank could mean everyone going to their local bank to take out their money. So you might have heard of like the runs on the bank that precipitated the Great Depression. So people going, everybody getting worried about their money, going to the bank and taking out their money is called a run on the bank. But it could also mean that someone did their morning exercise on the side of the river, on the side of a river. So literally they are running on the bank of a river. So it's a run on the bank of a river. Thus, the meaning of the word bank is dependent on whatever comes before the statement, a run on the bank. So if we put people took, it might mean one thing, but if we put she took, so she took a run on the bank, of that river, it might mean the other thing. So what matters is that the state of affairs that actually exists, so the ontology of the state of affairs that we're talking about, depends on the context. But the context did not cause the state of affairs to exist. But anyway, those are the two ways we can think of contextuality here. So again, the take-home message for this is that hidden variable theories of quantum mechanics must accept contextuality. So the Bell inequality says they also must be non-local, and we'll get into that in future videos. But for the purpose of this video, a hidden variable theories of quantum mechanics must accept contextuality, and that's what the Kochen-Specker theorem talks about. So the Stanford Encyclopedia on this, which is this one here, this Karsten Held, goes through some of the ways that you could try to escape the Kochen-Specker contradiction by sort of denying one of the other three postulates. So remember, our postulates were that were value definiteness, non-contextuality, and observables. So it goes through some ways you could maybe try to escape it by denying value definiteness or observables, but what you end up doing is sort of then you're just throwing out your hidden variables theory, which was what I was getting to up here in my analogy here, where we either have to accept contextuality here, or we have to throw out the sort of realism of the hidden variables. And so what you end up needing if you want a hidden variable theories is you want to throw out the non-contextuality postulate. You want to say that contextuality does in fact matter. But anyway, that was what I wanted to talk about in this video. In the next several videos, I'm going to discuss the pilot wave theory of quantum mechanics, or the pilot wave interpretation, and show kind of how they take this contextuality into account and show that they can be a hidden variables theory while also taking contextuality into account. And it also takes in the locality into account as well, or non-locality rather. So we will see that the pilot wave theory is contextual and non-local. But anyway, I hope you found this video interesting, and I will see you in the next one.